Hey, this is Hunter. We're going to look at the refraction exercises. You have some water here, and you have a lady who's about to dive into the pool, and she sees a coin down in the pool. So we know that light, when it comes through, is bent, and it kind of looks like this. And she doesn't like to open her eyes, so she has to just rely on her initial observation of the coin as it was made in the air. So obviously, she's going to have trouble trying to find this. We're going to draw our normal line here, and we know that this angle is 40 degrees because this is air, so we're going to say N1 is equal to air, and N2 is equal to water, so it's 1.33. They want to know what is this angle that the light from the coin travels up to the surface. So to do that, we're just going to say that the sine of the angle with the water, so that's angle 2, is equal to N1 times the sine of the first angle, which is with air, all over N2. N1, remember, is 1.00 for air, so sine of 40 degrees is the angle through which that's coming through. So make that look like sine a little bit better. And then N2 here is 1.33. So if you do your math, you're going to get the sine of the angle is equal to 0.483, and so you get a final answer of 28.9 degrees. And do know that you need to have your calculator in degrees. So if it didn't come out right, probably go back and do it again. The other thing is make sure when you solve for this, you're doing the angle is equal to the inverse sine of 0.483. So you have to hit second sine or do the inverse sine function on your calculator. For the next problem, here's an interesting trick to try. You can place a penny in the bottom of a cup and stand so the penny is just out of sight. So here we would have just an empty cup. You put a penny down in the bottom and then you stand so that you just, when you're looking into this, you don't see the penny at all. So it's kind of blocked off. When you fill that cup with water, though, what happens is you get a bending of that light, and now you are able to see that penny because of the bending of the light coming through the cup. So if you look into the cup at an angle of 70 degrees, at what angle to the normal does the penny need to be located in order to just for it to appear in the bottom of the cup when it's filled with water? So another Snell's law problem here, we've got N1 sine of the first angle is equal to N2 times the sine of the second angle. We're going to solve this one again for sine of angle 2. We're going to look for that second angle. That's equal to N1 sine of the first angle, all divided by N2. Our N1 here is for air, so it's 1. And then we do the sine of that 70 degrees. So that would be to the normal here. So this angle right here is 70. We're going to divide that by N2, which is 1.33, since that's the index of refraction for water. If you solve for sine of angle 2, we're going to end up with 0.707. We'll do the inverse sine of 0.707, and you should get an angle here of 45 degrees. And so that would be the angle down on this side, so right here. Next question says Rohit makes his girlfriend a romantic candlelight dinner and tops it off with a dessert of gelatin filled with blueberries. The blueberry appears at an angle of 44 degrees to the normal in air, and it's really located at 30 degrees to the normal of gelatin. They want us to find the index of refraction for Jello. So here we've got N1 sine of the first angle is equal to N2 times the sine of the second angle. Here we are solving for N1, so N1 is equal to N2 sine of the second angle all over the sine of the first angle. Our N2 here is air, so it's 1 times the sine of 44 degrees, all divided by the sine of 30 degrees. And when you're done, you should end up with an index of refraction for the Jello of 1.39. And that is number 3. Let's go ahead and take a look at the next one. So our next problem says a jeweler has to decide whether the stone in Mrs. Smiglowski's ring is a real diamond or if her soon-to-be husband is a cheapskate and it is just zirconia. So anyway, he measures the critical angle of the gem and finds out that it's about 31.3 degrees. They want to know, is it diamond or is it cubic zirconia? So to find that, what we'll do is we're going to use our equation again, N1 sine of the first angle is equal to N2 times the sine of the second angle. On this one, we're going to solve for N2, so N2 is equal to N1 sine of the first angle all over the sine of the second angle. N1 is 1, and realize that now we're doing the critical angle. So here, this is sine of 90, and it is divided by the sine of that critical angle. So instead of angle 2 here, we'll use our new equation, N1 sine of 90, which is typically with air. And then this is N2 times the sine of the critical angle. So here's that critical angle. Let's plug everything in. So now we've got 1 sine of 90 all over the sine of the critical angle, which is 31.3 degrees. If you solve for that, you'll find out that it is 1.92 and somebody is in a lot of trouble. So that is number 4. Let's go ahead and take a look at the next one, which is number 5. It says the index of refraction of ethyl alcohol is 1.36, while the index of refraction of water is 1.33. They want to know, does it travel faster in alcohol or does it travel faster in water? So for this one, is, let's see what it is here. And so we know here it's got to be the water because the water has a smaller index of refraction. So this one is water and it has a smaller index of refraction or a smaller n number. They want to know what is the speed of light in each. So here we're going to have the speed of light in alcohol, and that's equal to the speed of light over the n value. So this is 3 times 10 to the 8th, all divided by the n value for alcohol, which is 1.36. And so we end up with 2.21 times 10 to the 8th meters per second. The speed of light in water, so we'll just put H2O here. Same thing, so we're going to do 3 times 10 to the 8th, but this time we're going to divide it by 1.33, and you'll see that there is a difference. It's 2.26 times 10 to the 8th meters per second. And so those are your answers for number 5. Let's go ahead and take a look at number 6. Evan has taken Eva out to dinner to propose marriage, and he's hidden the engagement ring in her drink as a surprise. When she finishes her drink, she spots the ring beneath an ice cube. If she looks down into the glass at an angle of 61 degrees, but the ice cube refracts the ring at 42. What is the index or refraction of ice? So for this one, again, N1 sine of the first angle is equal to N2 times the sine of the second angle. So let's solve for N2, the index or refraction of ice. That's going to be equal to N1 sine of the first angle all over, sine of the second angle. Our N1 here is air, so that's 1. We're going to do that times the sine is 61. That was our first angle. And then we're going to divide it by the sine of 42. So when you do that, you end up with an index of refraction of 1.31. And that is number 6. For the next question, it's number 7. It says, in her bedroom, Mia has a fiber optic light that glows as hundreds of fiber optic cables are lit from below. If each fiber optic cable has an index of refraction of 1.48, what is the critical angle that the light must enter in order for total internal reflection to occur? So for this one, we know that N1 times the sine of 90 is equal to N2 times the sine of that critical angle. And so let's solve for the sine of the critical angle so we can actually find that angle. To do that, we're going to say the sine of the critical angle is equal to N1 times the sine of 90 all over N2. N1 here is air, so it's 1 times the sine of 90, all over N2, and N2 is 1.48. So that gives us a value of 0.676, and that is for the sine of the critical angle. So our critical angle then is the inverse sine of 0.676, and so we end up with a critical angle here of 42.5 degrees. I think that is what we wanted. The next one says, explain why total internal reflection is important. It's important because if that light is not totally internally reflected, it's lost as it reflects out of that fiber optic cable, and that cable wouldn't light up as well. So that one is number 7. And at that point, we've got number 8. Here we've got Spencer the cat enjoys watching the family goldfish from the top of the tank. If the goldfish swimming in water appears to an angle of 28 degrees as seen by Spencer, what is the true angle of the goldfish from the normal? So we're going to do the same thing we've been doing. N1 sine of the first angle is equal to N2 times the sine of the second angle. We're going to solve this one for the sine of the second angle, and so that's equal to N1 times the sine of the first angle, all divided by N2. Our N1 is 1 sine of 28 degrees, and then N2 is 1.33 for water. And if you do your math, you get 0.353, but that is the sine of the angle, so we need to do the inverse sine, so we can just get the angle number 2, and that should be 20.7 degrees. And that is the end of the problems for this section.